Hello everyone, my name is Konstantinos Kanavouras and today we're going to talk about reflection in C++ and experimenting with reflection in C++. So in this talk, just to give you an overview of the agenda, we will start with the general idea of what reflection is and some information about its current status in the language. Then we will move on with a very common application of reflection, which is serialization and deserialization. So converting data and structures from memory into another binary, for example, representation. And then we will combine those two concepts, so reflection and serialization, to create a new library that depends on those modern and future concepts of C++, basically. And then we will move on with some thoughts and conclusions. Now, this is not a reflection talk. We will not go into detail about the history, the rationale, the implementation details of reflection. We will not discuss about how reflection works and what kind of and all the things you can do with it. Because for this there are already a lot of talks that have been done, and reflection is a topic that's been discussed for quite some time in C++ now. So if you're interested in learning more about how you can use reflection and some of its more common applications, you can watch one of these talks. These are some of the more recent ones by the people who actually work on the drafts and the technical specifications for reflection. In this talk, we will talk more about experimenting with reflection, what you can do as a developer right now with reflection, what you can do in the near future, and how you might take advantage of it to work on a very specific use case, which is serialization. So, yeah, what gives me the right to talk to you about these things? I'm an electrical engineer by trade. Now I'm doing my PhD in the University of Luxembourg, and I'm working on very small satellites. And with these very small spacecraft satellites, it's always very interesting to see new programming techniques that can basically reduce your development time without a big impact in reliability and safety of your code. So I'm technically not a C++ professional, but I can get you through some of the experiences I had while trying to work with reflection and some libraries and serializations and things that we need to do in our developments which are intended for spaceflight. So without further ado, let's get started. So reflection is a C++ feature that doesn't completely exist in the standard C++ yet, and it's not implemented in major compilers fully. So there are a bunch of drafts and proposals to implement it in C++. And for those of you who don't know the term, I will give you a definition from one of the proposals that have been published for C++. And this proposal says that reflection is the process of obtaining metadata. What is metadata? Metadata is data describing some other primary data. Let's look at an example in the context of C++. So I have a class here. This class is called toast, and it has some values, some data members, and it also has a function. And in the context of C++, I would describe the primary data, the values that we are interested in. I would describe them as these numbers right here. So the values of the data members, the values of the variables in this case. And the metadata, the data that describes this primary data, is pretty much everything else. So right now in C++, we have a bunch of ways to access this primary data, a bunch of ways to get the value from variables, but it's not always so easy to get this metadata. For example, metadata here would be that this structure is a class. It has the name toast. These are the types of variables. These are the names of variables. These are the access modifiers, and so on. And Right now in C++, for example, it is easy to get the types of things. So you can use decl type and get the type of any variable and play with it. You can do conditionals and so on. But some things like access modifiers, argument lists of functions, names of variables, maybe it's not so easy. And this is what we want to achieve with reflection. We want to get access as complete as possible to these kind of metadata, which are related to pretty much everything that's not a value. And we can have metadata for classes, for types, for variables, for functions, for namespaces, modules, and so on. And this is, for example, something that you cannot do in C++ right now. If you have a class or an object of this type toast, a very simple example of reflection, of reflecting on your types would be to have a function, a standard library function called getMemberVariables, and this function would return an array of the variable names or variable attributes information of this object or of this class. So you would call a function and get all of the data members of this object here. The same way you would do this for variables, you could also do for member functions. So here you would have a function that returns maybe the public member functions of an entity, and in this case it could return like a standard structure member function, and you would be able to get its name, its return types, its argument types, the number of its arguments, and you would be able to call it however you want. And this is the idea behind all the reflection standards, that you want to access the kind of type information, type hierarchy, and information about other entities in C++. And you can take this concept to the extreme if you want. So there are this is an idea. We have this class, and it has two functions, caller and callee, and callee prints some information. So it prints who am I, where am I, so in which class have I been called in, and by which function have I been called, so kind of a backtrace thing. And maybe with an idea of reflection would be that this actually returns the name, so I am in callee, and you see the function returns its name basically. I'm in toast, so it tells you in which class you are in and by which function you have been called. So in this case, callee has been called by caller, so you would get an output called by toast caller. And this is the general idea of what you can do with reflection, and there are a bunch of either generic or niche applications for it. But a very nice summary was given by Andrei Alexandrescu in one of the talks I referenced earlier. And it's this quote that we must look at increasing leverage, more correct behaviors from fewer lines of code. So reflection is basically one of those C++ features that promise you that they can reduce your code, that you can reduce repetition, that you can use reflection to get information about code you've already written, and you know about the don't repeat yourself principle and stuff like that. And there is a bunch of usefulness here, and the thing I'd like to focus on is that we already have a bunch of libraries that would like to do something like this, but take a lot of workarounds or do a lot of compiler trickery. And having reflection would make some things that are now very complicated, they would make them very easy, and they might prevent, reflection might prevent a lot of duplication, especially when you're writing something that needs to handle the structure of a class or of an object. Now, as I said before, in general, for reflection, for metadata in C++, we already have some mechanisms that can work with it. And already at runtime, there is this keyword here, the type ID. So if you Google how to do reflection in C++, you will see a bunch of results. And this type ID thing, it might be one of the first results. And indeed, type ID can give you the name of a type. So something that normally you wouldn't have access to in C++. So you have access to values. You don't have access to names of types or names of variables in your binary. But with type ID, you can get the name, you can get the hash, you can get other information about the type of your variables. And we see here the output in mangled format for C++. However, this thing is quite limited, and one of the first of all, it returns all the names of types. So it's not, you cannot not do a lot of introspection on types if you want to. But also it's kind of runtime only. If you try to use something like this at a const-expr environment, you will probably not get very good results. You will get a compiler error. And it also possibly requires RTTI, runtime type information, which is something that might cause an overhead that you may not want to have in your binary files. And so this is a runtime mechanism. It might be good for some use cases. Maybe you have some type hierarchy that you want to discriminate, but it's very limited in terms of flexibility and functionality. So if you move forward in the story of C++, you see that with template metaprogramming and with all the new features being added, we have a bunch more reflection utilities and methods that we can use. For example, we have conditionals on types, and we have templates, and we have sphenae. And already you can start structuring your code based on how types are defined. And this has given us a lot of power, especially in what we can do with libraries. We have already very generic libraries in C++ right now. And then we have constraints and concepts. And here we actually start going deeper into how our objects are defined and what they can do. And here we can have something like duck typing, for example. But again, all these implementations and these standards, they talk about conditionals and they talk about checking. You still cannot extract, for example, the number of data members of a type or the names as strings. So the C++ community has been thinking on how to expand this kind of reflection and how to make it even more powerful for some time now. And there have been a bunch of proposals on different implementations for reflection. And here I'm going to show just some of the more recent ones, but I have a couple of links if you want to look at the whole story on how this thing has been going on and how it has been evolving over time. And the first proposal that I'm mentioning here is scalable reflection in C++, published in 2019. And this proposal defines a couple of new keywords for C++, so reflexpr and expr-id. And what reflexpr does is basically it gets the reflection of a type, and this reflection of a type contains the metadata of this type. And as soon as you have this metadata, then you can use a bunch of standard library functions that are defined by this proposal to work on this metadata of this type. So for example, here we have an enumeration, and we're getting the reflection, the metadata of this enumeration, and we can get the members of this enumeration, the names of the members of this enumeration, the values of the members of this enumeration, and so on. So we have full access to the metadata and the primary data by using those two keywords. And this example, this function here that I took from the draft, this is a very standard example that you will see in a lot of these talks, which is how to convert an enumeration value to a string. This is a very popular Stack Overflow question for C++, something that people want to do a lot, and something that would, at least if you use it for diagnostic purposes, would might help your development process by a lot. So yeah, what this function does is that it converts an enum to a string, an enum value to a string, and the way it does that is that it's templated, it gets the enumeration value, and then it goes through all the members of the enum, and if one of the members matches the value that you have provided to this function at runtime, it returns the name that's given by reflection. So that was published in 2019, and there was another draft technical specification published in 2020 based on this proposal and another one, I think. And this technical specification also, I think, made its way into an ISO standard, which is the C++ extensions for reflection. A few years later, we got the second revision of the previous draft, which is Scalable Reflection C++. And here we had a couple of changes, more notably a change in symbolism. So now we use this caret operator and this format to do reflection, and some other changes as well. And actually, just a month ago, there was this draft published, so reflection for C++ 26. And this proposal is basically a subset of the previous one that's, and with slight modifications, that's actually intended to go into C++ 26. So we'll see whether that will happen or not. But there are interesting reads if you want to go into the rationale and the functionality of the proposed reflection mechanisms in C++. And by the way, the technical specification, the ISO technical specification, is also available in C++reference.com. So most of the links have articles and have documentation in them, so you can get a more general view of what this technical specification contains. So all of this was intended to give you a general idea of what reflection means and where it stands right now from a formal and C++ standards point of view. However, reflection is a very often requested feature, and there have been a bunch of people, of library developers, that have tried to work around the limitations of C++ compilers and implement at least a subset of reflection on their own. And a very good example to show you this is the enumeration to string question. It's a very popular search query. And if you go through the answers to these questions, you can find that they usually belong to one of those categories. So the simplest way would be to store the strings in a kind of container, so that the variable name and the string representation is separate. So that's a simple way to do it. You have to repeat the same thing 2 times, but it works. Then there is another implementation, which is that some libraries define functions or preprocessor macros that basically store the strings in a container on their own automatically. So you don't use compiler features, but you don't need to repeat yourself. There are some other implementations that do code generation. So there is an answer that contains a CMake tool that reads your code and then generates another piece of code that contains the strings that you want. And there are some also clever workarounds that use newer C++ features and user-defined letters and so on. But the top answer that you get here is a small library called Magic enum C++. And what this Magic enum library does is it promises you that you can convert an enum to a string without any extra code and without any extra boilerplate. So if you have an enumeration, for example, color, red, green, blue values, and you want to convert it to string, what the library tells you is that, okay, you can define your color here. So a variable, enumeration type. And then you can call this function here, so magic enum name, color, and then you automatically get back a string. And this is just with this single line, somehow you can convince the compiler to return to you the name of this type, basically, as a string. And this is something that should not normally be possible with the C++ I know. And you can do the opposite thing. So if you have a string, you can also define your type, and it converts it to an enum value and an enum type. And when I saw that this was possible in just a line, I was very curious to see how it works. And the answer is that it does some very nice compiler trickery, and it depends on some compiler specific capabilities. So in this case, it's this magic identifier, pretty function from GCC, and there are similar things you can do on CLang and MSVC. And what this magic identifier does is that it gives you the name of the function you are in. It gives you the signature of the function you are in, to be more specific. So you could get enum name, you would get the return value, standard string, and you would also get, because this is a template function, you would also get the template arguments. So in this case, you would get the exact value of the color. And if you're passing an enumeration value, you would get the name of this. So if you call this function with the red value, you would get back this signature, so standard string and enum name, and then the template arguments, so C equals red. And then you can do some very simple string parsing to get this red value. And this only works at compile time, so you need to have your value specified in a template. But the library also does some trickery when it puts up, so it puts all the enumeration values inside the map, and then you can access everything at runtime as well. So this is how the magic enum library works, and this is how it pretty much does some form of reflection, but without using standard C++, and by doing a lot of trickery behind the scenes. So there is a lot of work and code that is needed to make this actually work. And here I would also like to mention that for many use cases, reflection can be considered as a convenience feature. It's not something necessary to have. It's something that makes our development faster in some use cases. And if you have a more complex program or some more mission-critical piece of safety-critical piece of software, maybe you do not want to tie the functionality of your software to the names of your variables. Maybe you want to be sure that if you do a refactor and you change this blue to cyan, your end user will not see any change. And this is not something you would use the magic enum library for. But for many use cases, especially if you're doing diagnostics, if you're doing serialization, as we will see later, reflection is a very powerful tool to have under your belt. So this is one library. This is magic enum. Let's see other reflection implementations. There is boost describe. So this works based on macros. So it defines some preprocessor macros and functions, and you have to define your objects, and then you have to tell the library that, okay, these are my objects and these are its data members. And then again, a lot of work behind the hood, but you also get access to the names of the data members, the sizes, the types, the counts of the data members, and so on. And this is completely reflection. Then there is another approach from Boost PFR, which is a simpler, more limited version of reflection based on template metaprogramming, which also allows you to get the members of a type. So in this example, we have a structure with 3 data members, and you can just simply print these fields and the number of these fields without any extra effort. And this is also weird. This is not something that should be very easily possible with standard C++, but it actually is. And I was also very curious to see how this can work. And the answer is that this depends on structural bindings in C++. So if you have a simple type, maybe an aggregate, you can use structural bindings and basically extract the values and the types out of your objects. And here, for example, we have the structure, and we do a structure binding with 3 variables, then we can print everything quite normally. And there is a blog article you can read if you want more information about how to do this in C++ 17. But you also need to do a lot of work behind the scenes to find out how many members you need. Maybe some Sina is involved here as well. But it is something definitely possible, and there are libraries that do this. So yeah, the advantages of this thing is that it works with pure C++ 17, so no compiler-specific features needed, but it's limited in capabilities, doesn't work with all types of objects, and the hardest thing, you cannot retrieve these names right here, A, B, and C. We can still not print them as strings. So this is the approach of the Boost PFR library. Then we move on. We have a couple of other libraries that do reflection in current C++. So there is RTTR, a runtime reflection library. Again, same concept. You need to tell the library about its metadata. We have REFL CPP, similar concept here as well. And then if you go deeper into reflection, you will actually find that some compilers have implemented it as a separate feature already from the compilation stage. And if you go, for example, to Microsoft's C++ compiler, you will find a couple of articles explaining that it has very specific functions that can do quite powerful reflection. And for example, here is the standard example of converting the enum value to a string. There's a cyclic compiler, another experimental C++ compiler, and it also defines some reflection features with its own custom syntax. But then there are also people that have implemented reflection from the drafts and proposals that I showed to you before. For example, this is a popular implementation. This is an LLVM fork by the Log3 company who specialize in very new C++ features. And they've actually implemented this standard with REFL Express with a few modifications. And if you go on this repository and you check their wiki, you will see that they have a bunch of information on how to use reflection and extra features they've added and so on. And there is a talk by Andrew Sutton that explains these concepts. So this is very nice to have. It means that you can already kind of experiment with reflection on your own based on the standards. I think this is also available on Compiler Explorer if you don't want to compile the compiler yourself. So there is also another fork of CLang of LLVM, this one by Matus Hochlik, and this is an implementation of the technical specification that's an ISO standard, I think. And Matus has done a lot of work behind the scenes to actually create a lot of examples. And the mirror library that makes calling some standard reflection functions a little bit easier. So here you can see the standard enum to string implementation, and he has also done a talk in this conference last year about the design of his API and his implementation, and a bunch of examples and use cases for it, which I also highly recommend. So this is how you can do reflection today. Now let's talk about serialization and deserialization, or sometimes it's called marshalling and marshalling, or packing and packing. There are many debates online about which term is suitable for which purpose. I will just call it deserialization and call it a day. So what serialization means in the context of today is that we have some data in our program, in our memory. We have some kind of structure, and we want to convert this data to either store it permanently or to move it somewhere else through a communications channel. And then after this data is moved, we can get back into our memory, our software representation of this data through serialization and deserialization. And there are a bunch of ways, a bunch of reasons that you might want to do this. For example, you might want to store the data because you are a video game developer and you want to store the save files. Maybe you want to transmit the data or a structure or some information to another application running on the same computer or in a different device over a wired network, over a wireless network. Maybe you just want to look at the serialized data for diagnostic purposes. Maybe you want to compare objects, but it's mostly two categories, storage and communication. And depending on which field of software engineering you are working on, you might be looking at reflection pretty much every day in your daily work. So this is something that's already been done. This is something very popular. Let's see how people do it and what kind of protocols, what kind of ways of formats they use to serialize data. And there are a bunch of formats, binary formats or plain text formats to do this. So if you wanted to use a serialization library just for yourself, so a naive implementation would be to just say the names of the variables and then the values, so ID 7, temperature 32, and so on. JSON, a very popular format in web development. You can define objects and arrays in a more structured way. And if you want a more efficient binary format, there is a BSON implementation of this thing. If you want to be more flexible, we have XML, and then some specific serialization libraries from other languages, like Python Pickle. They define their own formats, or protobuf, protocol buffers by Google. They also define a format, and this format has its advantages and disadvantages. And in some cases, especially if you're doing communications, radio frequency communications, you might be inclined to design a custom protocol, custom serialization format for your own specific use case. So reflection is so popular that we have a bunch of libraries for it. And its library makes different trade-offs and has different use cases and disadvantages or advantages. But I think we can make a couple of important distinctions on how each of these libraries work. First of all, on the data format and on the serialization format that you define for them. So in some libraries, like the protocol buffers, the library tells you the format that it will store your data in. So protocol buffers defines a binary specification. It's a very good binary specification. You can have versioning and so on, but you're locked into the specification. You give it the structure, and it tells you that this is the binary format. In some other cases, you might want to define the data format on your own. You might want to say that, okay, I want this integer to take 4 bytes and be big endian. I want this float to be stored as an IEEE float. I want the string to start with its length and not have an null termination character. This is another use case. Then there is another distinction, which is whether this library can only serialize and deserialize things at runtime, or if it can run on a const expert environment as well. Usually, for this context, we will probably not need to serialize stuff at compile time a lot, but maybe it's a nice thing to have. Then a bunch of those libraries are not technically libraries. You give them a format and they generate the C++ code for you. So they compile the data format and they generate C++ code for you. But there are also other libraries that don't require this preliminary step, and they just run entirely within C++ and entirely within the binary that you generate. And then a final distinction is that some of these libraries, these programs, have implementations for different languages. So if you need to interface between different systems written by different people with different use cases, you might want this kind of capability, which is very, very common to see in serialization. Or there might be libraries that are built mainly for C++. Let's look at a couple of examples. So this is the Google protocol buffers. The way they work is that you define your structure in a nice file. So those.proto, some boilerplate, and then this is the type that you want to convey. So 32-bit integer, ID, float temperature, string review, and here you assign some IDs to those types. And then as soon as you have this specification, you run a terminal command, and it gives you a bunch of auto-generated C++ code that you can just include in your project and compile things immediately, serialize things immediately, and everything is type checked, and everyone is happy. So this is the compilation approach. Let's look at the runs within C++ approach, also used by a lot of serialization libraries. And this is a common approach that you have a structure with its data members. And then again, you need to tell the library that, okay, these are my metadata, these are my data members, you know about them, now serialize them as you know. And this is a very common way to do this kind of thing. So this was for the serial library. Another example for the bit-seri library, again, similar concept. You define a function that tells the data members, the metadata, to the library. But here I want to show this example because you specify the binary types by hand by yourself. And there are some use cases where you might want to have this kind of more fine control over how your data is serialized. This is another example from not a C++ library, from a Python library called construct. And I found this interesting because this follows a slightly different approach. So you have your object to be serialized with all the data, but then you have another object which defines the structure. And here you don't have the API of the library does not give you a function. It tells you to create a new object, and then with this object you can compile your primary data, and you get back a similar result. So this is a fully user-defined data format that you can work with. And finally, there is this Sista library, and this one allows you to serialize at just one line without giving it any metadata. So let's look through this example. We have a structure, we define it, we give it some values, we define an object with some values, we use a weird kind of string here, and then we call just this one line, so a buffer equals the result of Sista serialize, just one line, no extra boilerplate, and it actually gives us back the serialized string, so these are some binary non-displayable characters, without any other information. And the way that this library works, is something we saw before. So it's a similar thing to boost PFR. We have structured bindings, and this library does a little bit of reflection behind the scenes. This means that it can serialize your structs, but it's kind of limited to some aggregates and maybe not very flexible. And again, based on your use case, you might be very happy with something as convenient as this, or you might be not happy at all. Finally, let's look at serialization in practice. And this is an example from a small satellite project. And what the satellite needs to do is it needs to serialize telemetry to send back to the Earth and deserialize telecommands that it receives from the Earth. And the ground station on the planet needs to do pretty much the same thing. And if you look at the code that we wrote for this satellite, you can see that we have a little bit of repetition. So in this case, in a function that parses the telemetry, we might have an event definition ID that's the result of a read enumeration function, and another variable is a result of a read function from a string or a buffer. Then if we want to generate this, if we want to serialize and not deserialize, we do the same thing, but the opposite way. So we append instead of reading. But then the ground station, we're using a different kind of software, which requires those arguments to be given in XML format. So we have a entirely different specification. And all of this is based on some external paper documentation. And this is already 4 times that we're seeing the same thing repeated. And it's also not easily searchable. You cannot do Control F on this code, you cannot, the event definition IDs, these variable names, they are used pretty much everywhere in that code base. So you need to know as a developer or a reviewer that, okay, I need to I need to change this on all parts of my code or have very well structured tests for this. So ideally, what I would like is to just have one central piece of, one central point of documentation, and based on this, generate, have the compiler generate code, have a library generate code, or structures or convenience functions around it. And maybe it would be an interesting idea if even you don't write C++ code, but you give this kind of XML definition to your C++ library. It reads this XML definition at compile time, and it becomes able to generate some structures for you and parse and generate the binary format of those things completely on its own as a C++ library, with everything done at compile time, modern C++ const texture, optimized, and so on. So today we will try to move forward towards that direction. We will not reach the XML reading goal, but we'll still try to see if we can make a library that conforms to some of the specifications. So a user-defined data format at compile time that runs entirely within C++ with minimal repetition, and a couple of other nice to have features as well. So let's go ahead and create yet another serialization library. Now I've been working on experimenting with reflection and creating a library like this. It's called ok-serializer. You know, developers are not very good with names. This library is meant not to be used for production or not to be meant as something serious. It's just meant as an experiment and as a tool to see how we can improve maybe already existing serialization libraries out there as soon as we add reflections and C++23 to the mix. So it's not supposed to be a good serializer. It's supposed to be an okay-ish serializer, hence the name. And let's start with going through the thought process of working with a library like this. And first of all, we want to use very bleeding edge C++, and we want to use reflection. We want to see what a reflection can do. So we saw that there are a bunch of implementations of reflection at compiler level already. And when I started working on this, the most recent one was by Matus Hochlik. So this is the one that I started using. With a couple of updates. I think this was written for CLang 15, but I wanted to use more contemporary C++ features, so I did a small merge with CLang 17. So we have our compiler. Let's talk about the structure of this library. Let's talk about maybe the requirements of this library. So pretty much what I showed you before, almost everything should be possible at compile time. Another requirement is that ideally this would be used in embedded systems, so a system with a low footprint, so there is a requirement for no exceptions. There are a lot of discussions on whether exceptions are okay or not for embedded systems. I will not go into this. I just avoid all the debate by saying no exceptions. Instead, we will use this new standard expected type. Also, no dynamic memory allocation, so using standard library containers is not necessary. Using new and malloc is something we will not be doing in this library, again, to support low footprint embedded systems. And no fancy compiler features, no specific things that are not standard C++ or experimental C++. The end goal for today will be to write a single line and serialize an object into a JSON format. And this is what we will do. But the long-term goal for this experiment is pretty much what I showed you before. So we want to take an XML definition and serialize it completely at compile time. Now, this is not something entirely new. This is not something novel. Similar concepts have been done before. For example, you can find on GitHub on the mirror repository by Matus Hochlik that he has a couple of examples of serialization and deserialization with JSON and reflection. And there was another serialization library based on compiler time reflection that was presented in CPPCon actually last year. But here I thought this would be an interesting experiment to go you through the thought process of developing a library like this, of experimenting a little bit more and seeing if we can actually get those more specific requirements to work for us. So let's get started. The first thing that I would like to do for this library is to actually test reflection to get our compiler installed and see if it's working. And that's what I did. So we have a test file here on CLion. And what I've done in this file is I want to do the classic enum value to string example. I used some code by Matus Hochlik. This is a slightly complicated way to do the enum to string implementation with reflection. It uses recursive functions. Maybe you can do it faster, but this is good enough for our purposes. And it uses completely standard technical specification C++. So let's make an enumeration, and I can do an enum color, and maybe I have mauve, cyan, and orange. And then what I can do is just do standard output and enum to string. The template should be deducted, so color mauve. I'm getting a compiler error, but it's printing everything correctly. And yeah, you can already see that CLion does not really like reflection, but it actually works. Now the question here is, we can do this at runtime. Can we do this at compile time? So let's try with static assert, and let's see if enum to string color mauve is equal to orange, and this comparison should work. And okay, we see that the static assertion failed, so we have the negative test case. Let's do the positive test case. And we see that everything compiles, so we know that the static assert is working well enough. So we have reflection working. This is good. We can experiment, do a lot of other things with reflection. Now let's go into making our serialization library. And the kind of API that I would like to have with this is looks something like this. So we have a serialize method. This serialize method explicitly takes the binary format, the serialization format that we want, and then we pass our output as a reference and the value that we want to serialize. So this design decision here, this is intentional because if you're working in wireless communication, for example, you want to be very specific about the kind of format, the data sizes that you're using, and so on. So here I'm making it very specific, but if you want, it is very possible to deduct the serializer that you want to use from the types that you are passing. Here I'm also using a buffer as an output, so I'm saying that, okay, this is a dynamic kind of dynamically expanding output that's connected to a standard string. And if I run this, then the string will equal to high. And we can do deserialization in a similar way. So deserialize, here I also specify that I want little NDNS for my input, and I give a string as an input, and I get back my value as an integer. Now this is a bit heavy to do because you need to specify your buffers. If your use case is standard strings, and we will focus on standard strings for the rest of this talk, you can just call serialize to string and you get back a standard string, or deserialize and you can just directly pass a standard string inside. Now, at this point for this library, I would like to focus on this a little bit, on these inputs and outputs and how this is done. And I'm sorry if this is not perfect C++ code. Maybe there is a lot of room for improvement, but it should give you the general idea. And there are also a bunch of implementation details hidden in the source code. But let's see the general idea for inputs, for inputting binary data to deserialize. And in this case, for inputs, I have a generic input class that takes as argument an input range, so a C++20 input range, which is by default a string, which means that you don't really need to mess with iterators anymore. You can just pass a standard string or an array or a weird ISO buffer maybe inside here, and everything should be parsed correctly. And we can do a similar thing for the output, so we can define a range type of output for the serialization library that works based on an output range, and the output range gives us some very fancy stuff that we can do with iterators that avoid having to handle a lot of edge cases. And this is what we want to do here when we are adding basically a character into our output. And again, here you can pass standard strings, you can pass string views, you can pass C-style strings, you can pass buffers and so on. So this is how we do input and output. And I will also spend a little bit of time on the binary types that we support. So we have unsigned integers in our binary format. We define how many bytes they are, up to 8 bytes. Endian, big endian, little endian, signed integers, variable sized integers. This is a Google protobuffer thing as well. Convenience type for enumeration values, floating point values, string representations prefixed by the length of the string, or C-style strings that have a terminator, which is usually the null character. And we also have a bunch of compound types, actually, which means that in the same serialization command, we can serialize many different types, one after the other, or we can serialize an array. And let's actually look at one example of this right now. So let's go to here, and I will remove everything. And we can, let's say, define a standard array of int 16, and let's say it has 68 elements for no particular reason, and we call it R. And let's fill this array. So R begin, R end. Let's fill it with 68, 69 in hexadecimal format. And let's also do a standard output. So, okay, serialize. And our serializer is length prefixed vector. And the length prefix vector contains elements that are unsigned integers of a width of 2 bytes. And then we should be able to pass our array just like that, std_handle. And I forgot to serialize this into a string, so I'm using the convenience function right here. The compiler is happy. Let's look at the output. And we get back our length prefixed vector, so we get back a bunch of highs prefixed by the length in binary representation. So in this case, it's the capital letter D, which represents the decimal number 68. And this is how this thing works. It should be able to work at compile time as well. And you can work with this library. We can already do some very simple serialization. A very small implementation details, iterating for the bundle type, which can have different serializers in sequence. We use tuple template arguments, parameter pack template arguments, sorry, and it takes a little bit of effort to iterate over them at compile time, but it's possible with parameter pack expansion. Now, another small aside for return value types, we're using standard expected, not exceptions, and we define a custom alias in the library for a result. So everything you get for deserialization gives you back a result, and this result might be the type that you actually want, so the deserialized type, or it might be an error. And there are some very nice monadic convenience functions in C++23 for working with std expected that make it quite fun to play with, if I'm honest. And then for serialization, for the reference type of functions, we are using an empty result, so we either return nothing or we return an error, so similar to kind of returning an error code. And if you look at what this parse error is, it's a structure that contains basically an error type, and the error type is an error code. And maybe in the future we can add some extra information in there if we want. Finally, there are some unit tests for this library, and if you're making a serialization library, it's always fun to see what we call idempotence. So you want what you serialize to be the same as what you deserialize. So if you get anything through the process of serialization and deserialization, you have the same thing in the beginning and the same thing in the end. And the CATS2 testing library gives you a lot of facilities to be able to kind of do that. Okay, so now we have a serialization library. This is nothing really new. Okay, a couple of C++23 features used, but it's serialization. It's fun, but it's not something terribly exciting. Let's add a little bit of reflection to the mix, and let's do the very simple thing that we want to serialize structs. So we want to serialize the data members of a struct more specifically. And for this, I'm using, again, the mirror library by Matus Hochlik, which depends on reflexpr. And I'm defining a function, serialized struct. It takes an object and an output, and we have here we have the reflection of our struct, so we call mirror, and mirror produces the reflected type. And as soon as we have this reflected type, we can call some functions from the mirror library on it, and we can get all the data members in the struct. We can loop through all these data members, and we can get their value, serialize this value, and get back the result. And you see that my code is not perfect. I forgot a couple of std forward things in here. Anyway, just a little point of attention. So in the previous examples, we had to define the serializer by hand. So we saw that here we had to define that, okay, this is the length prefix vector, and it contains unsigned integers of size 2. In a struct, we don't really have this. We need the library to kind of guess the binary format that it wants to use. And for this, we define a configuration object, and these configuration objects contain a templated default serializers member, which specifies that, okay, if it's a uint 8, it will get assigned to an ok-ser unsigned integer of size 1, and so on. And okay, let's see an example of this actually. I think I can get it to work. So let's define a structure. So a structure, and let's say it contains a signed integer a, and let's say a is equal to 104, and an unsigned integer b that's equal to 26913. And now I should be able to just call ok-ser, serialize struct. I have a convenience function, serialize struct to string, and oops, let me instantiate an object first. Okay, no compiler errors, that's a good sign. Let's run it. And we can see that the output is actually high. So if you go and put those in a hex editor, you will see that these values serialized with a big endian format, they should give back high with an exclamation mark in the end. So this is one way to do it. And you can see I also have this example here. We define the structure, just one line, and we get back our serialized information. Now here the library does the specification for us. So it knows that this is 1 byte, it knows that this is 2 bytes. Maybe this is something that you might not want. Maybe you want to be very explicit in what kind of type you want to use, and what kind of format and sizes, and maybe alignments, paddings, and so on. So one idea would be that you can change this configuration object that we pass at compile time, or maybe an extension to this library would be that here in your structure you have some pairs, so a pair of value type and serializer type, and the library kind of sees these pairs and generates everything accordingly. But long story short, we have reflection working, we have serialization working, but this is not something completely new. Already we see with structured bindings, we can do this in C++ 17. However, this time the implementation was very simple. It was just a couple of lines in a small function. But in any case, let's see if we can extend this further. Let's see if we can reach our JSON end result. So we can write a JSON implementation by hand. We will see why that is in specific. And we can add the standard JSON times a Boolean number strings arrays object. And we can try and serialize stuff with it. And already you can see that CLion is complaining in the object structure, because inside the object structure we do a little bit of reflection. So let's see if we can make this work. So remember, we had our structure, and I think I can do serialize to string, and I can pass a JSON object, and this is our serializer, and then I can pass my structure. Compiler doesn't complain. Let's execute this, and it works. And we can already see that with this single line, we get back a JSON representation. And the difficult thing here is that we got these values right here. We got the variable, the member names. And this is something that you probably cannot do in C++ right now, and this is kind of the power that reflection gives you. And if we want, we can get this a little bit further. So I can make an array of, ints, just 5 members, and this is 1, 2, 3, 4, minus 8. And let's give the name to this array. I can add maybe a substructure, so let's define one right now. And I can say float b equals 13.6, and I can give it a name. And now if I compile it, everything should work. And yeah, I get back all my JSON and nested things as well, a nice array. I could do strings if I wanted to as well, so everything works. Now the question is, can we do this at compile time? And the answer is probably yes. So let's do a static assert, and let's actually get this thing here and compare it with, actually I need to write this as a string, and so we're getting an error. I need to convert this to a const expr, and am I missing something? Probably not. And everything works, everything compiles. CLion is still complaining, but we saw that this assertion works, and this serialization basically can completely happen at compile time as well. And this is kind of the power that modern C++ can actually give you. And as a small aside, if this is something you want to do for diagnostics, to read that your objects, you can define an O-stream operator and just do this. So for this example, I've just defined an O-stream operator for pretty much every object that's not a string. And you can see that with this little bit of magic, you can just output structures as if it was Python. So this is the kind of power that you can get with reflection, and this is just a simple example with the current implementations, with a very quick work on a library. And right now it's a very rudimentary implementation of JSON. It's a manual implementation in order to get this to make it work with const texture, and it's just a serializer working. But you can further expand this, of course. And this brings me to the end of my talk. So we saw the ok-serializer library. It has a couple of interesting features. We were able to comply with the requirements we set earlier, and it's quite useful for embedded systems as well. So we can work with strictly no dynamic memory allocation and with strictly standard expected, no exceptions as well. So the embedded people will be happy. But there's still a long way to go if you want to get this into a kind of mainstream serialization or marshalling library. And there are some also interesting concepts that you can play with if you're thinking about the future of how this could work in C++ or what a serializer library like this could do ideally. For example, Java, PHP, they have comments, annotations that the code can actually read and influence its behavior based on that. So for the library itself, how does its future look like? Maybe we will get it in one of the space projects where I'm working. And the end goal for all of those things is to have this kind of single source of truth, whether it be code or an XML file or anything else, that allows us to define our telemetry and telecommands and do everything, all those things, parsing, generation, and so on around it. And this is an example of how you would do this, for example, in Python using the construct library. And then you can start thinking about other more complicated things and experiments you could do. So the interpreted languages have this thing called evaluation. You can evaluate new code at runtime. Could we do something like this in C++ for compile time? Like you pass the name of a variable or a data member as a string, and you get back what you want. It's slightly possible with the current proposals for reflection right now. Maybe it would be interesting to see this expand. There are safety arguments on this as well, but it's interesting food for thought. And the final thoughts that I have is that implementations for reflection exist, whether they are for the C++ that your employer allows you to use, or the C++ that you can get if you compile LLVM on your own, or if you use a Docker instance to do your own experiments that I will put up in the library repository. So yeah, you have the capability to work and play with these things. There is a bunch of references online. Most of the implementations that are online are for the slightly older versions of the proposals and drafts, so not updated with a new operator format and any other changes. But we have now this new proposal, which is active. There are revisions actively being done on it. You can check the GitHub for the proposal, and it also adds, instead of just reflection, it also adds a little bit of metaprogramming inside there. So there is a way to actually define new structures and new formats inside. So this is a synthetic struct defined by this technical proposal. Yeah, so that brings me to the end of my talk. Thank you very much for your time. These are my contact details. and I hope you enjoy the rest of meeting C++. Thank you very much.